Swayam Prabha. Digital India. Educated India.
Welcome to Structural Dynamics class. So in this class we will discuss about response spectrum analysis. So when do we want response spectrum analysis? So we do response spectrum analysis when we don't have time history available to us, and then for most of the buildings, so the response spectrum, design spectrum whatever is suggested in IS 1893 is available. So we can make use of that and find the maximum forces and maximum deformations which might occur in the structure using this response spectrum analysis. So response spectrum analysis uses almost same principles as time history analysis, but only instead of finding time history we will find the maximum values of the response. So let us go to the outline of the lecture, outline of the class. That first we will understand the building details and how we do the idealization of the building into lumped mass systems. Then we find out mass, stiffness and damping matrices, then dynamic equilibrium equation, then how to decouple these equations and model response from the response spectrum, and then we find the total response at each floor, and then we will solve one example problem. So building details, so as an input, so this is actual building, so we are converting this building into lumped mass system. So mass 1, mass 2, mass 3 at say floor height levels, mass 1, mass 2, mass 3, and stiffness 1, stiffness 2, stiffness 3. So we generate mass matrix, stiffness matrix and damping matrix. So we already know how to generate mass matrix, that is M1, M2, M3. All terms will be in diagonal and off diagonal terms will be 0. And then stiffness matrix we know how to generate it, and then damping matrix also we know how to generate it. And this is general equation of motion. So mu double dot plus cu dot plus ku is equal to applied force. So this applied force in terms of earthquake actions we use that as mug double dot. So when ug double dot is available we do time history analysis. Okay. And if the spectrum of this ug double dot acceleration is available, then we go for response spectrum analysis. So for decoupling this equation we use u is equal to phi and q. So phi is a space quantity which we call it as mode shape, and q is a time quantity. So if we substitute this in the above equation, what we get is m phi q double dot c phi q dot and k phi q is equal to mug double dot. So if we pre-multiply this with phi transpose, so this phi transpose pre-multiplication we are doing for decoupling these equations. So damping matrix is coupled, stiffness matrix is coupled. So that's the reason why our equations, 3 equations are coupled equations. So we need to decouple. This decoupling is done by using the orthogonality property of the mode shape. Now phi transpose m phi q double dot plus phi transpose c phi q dot plus phi transpose k phi q is equal to minus phi transpose m u double dot g 1 multiplied by 1. 1 is a vector. So due to modal orthogonality of m, c and q will become diagonal matrices. So now m11, m22, m33 these are diagonal terms, c11, c22, c33 diagonal terms, k11, k22, k33 diagonal terms of stiffness matrix. Now this is a decoupled equation. So m11 multiplied by q1 double dot, c11 multiplied by q1 dot, k11 multiplied by q1 is equal to m1 of 1 multiplied by u double dot g. So these decoupled equations will look like this, whereas this is corresponding to, okay, so force 1, force 2 and force 3 at those in that degree of freedom, sorry, in that mode shape. So modal analysis is converting n degree of freedom system into n single degree of freedom systems. So if we divide by mass, we get Q1 double dot plus C11 by M11 Q1 dot plus K11 by M11 into Q1 is equal to M1, this is modal mass, divided by M11 into U double dot. So this one is modal participation factor. Generalizing that, what we get is Qi double dot plus 2 zeta I omega I Qi dot plus omega I square Qi is equal to Pi Ui double dot G. So this Pi is participation factor. How much mass is participating in that mode, that much force will be applied in that mode. So it is defined as phi transpose M1 by phi transpose M5. So we discussed in detail about what is participation factor in the previous lecture. So that is time history analysis. You can refer to that for getting the clarity on participation factor. So usually for designers, design engineers, the maximum displacement is of more important for calculating the design forces. So hence from response spectrum we get these values instead of time history. So we get say Qi double dot plus 2 zeta I omega I Qi dot plus omega I square Qi is equal to Pi U double dot G. So U double dot G is a ground motion, P is the mass participation in that mode shape. So now what we get is maximum value of Q. What we want is, so whatever is the natural period or natural frequency of that mode, from that we study response spectrum and get the displacement value, maximum displacement value. If we multiply that maximum displacement value with participation factor, we get maximum displacement in that time history response. So let us assume that this is a spectral displacement curve of this acceleration time history. So we have acceleration time history. So from that we are converting that into, or we are calculating a response spectrum for that. So how to convert, how to draw response spectrum, we have discussed in response spectrum lecture. You can refer to that. So this is a spectral displacement curve. So natural omega is available with us. So T is equal to 2 pi by omega. So Ti means T 2 pi by omega I. So if we put first mode omega, we get first mode natural period. So we take that first mode natural period and then hit the curve at the location and then read spectral displacement value. So that spectral displacement value we use here. So that is the maximum time history response in that mode shape. And there is a mass participation in that mode shape which is given by P1. So spectral displacement we multiply with participation factor to get the maximum displacement which it is contributing to the total response. So spectral displacement is for complete earthquake. This one is for complete earthquake, but the particular mode shape mode has particular participation in the total response of the building. This we discussed in detail in the previous lecture of time history analysis. So each mode shape is contributing some extent to the total response. So that depends on participation factor. So particular mode shape has particular participation in the total response of the building. Therefore, the amount of displacement in one mode is given by, so this equation, SD multiplied by participation factor. This is the maximum response of that mode shape in that mode multiplied by mode shape values at different degrees of freedom. So then we will get Uij of T maximum value. So it is something like that. So J is represent the floor and I represents the mode. Now if you look at this one, each mode shape, so Q1 max is this multiplied by this. So these two constitute that value, Q1 max. Participation factor in that mode shape multiplied by spectral displacement of that mode shape. So this is maximum time history response in that mode. And then if we multiply with say mode values, so we get phi 1, phi 2, phi 3 of first mode, phi 1, phi 2, phi 3 of second mode, phi 1, phi 2, phi 3 of third mode. So if we multiply this Q1 max with this one, so we get this maximum values. Now how to add them. So we know that this maximum value is occurring at say some t 1 time, and this is occurring at t2 time, this is occurring at 3 time. So we cannot directly add. In time history analysis we were adding at every time instant all these values directly, but in response spectrum analysis we cannot add them directly. So we want most conservative estimate. So there are several techniques in adding these modal values. So we have two techniques which we discussed, that is SRSS method, that is called square root of sum of squares method, and then second one is CQC method, complete quadratic combination. So we discuss SRSS method here. So SRSS method is used when there is a distance between the mode shapes or eigen values. So if eigen values are very well separated, then we can go for SRSS method. If eigen values are in the vicinity of 10%, then we cannot go for SRSS method, we have to go for CQC method. So in the vicinity of 10% means what? Say if first eigen value is say 30 and the second eigen value is say around say 33. So then we have to go for CQC method. So if first eigen value is 30 and second eigen value is say 40, 50 or 60, then we can use SRSS method, that is called square root of sum of squares. So the total response at each floor, that as the maximum values do not occur at the same time instant, they cannot be added. Therefore two methods for obtaining total response. So one is SRSS method, second one is CQC method, which we are not discussing in this class. So that is uj is equal to u1j square plus u2j square u3j square. So that means what? So j is the floor level. So first floor level maximum value, first floor level second mode, this is floor it is telling. So first floor level second mode maximum value, first floor level third mode maximum value. So you add. So that means what? P1 J1 first mode SD1 square. So you add all these. So U1 U2 U3 we get. So this is the maximum displacement of first ground floor, maximum displacement of second floor, maximum displacement of roof in 3 degree of freedom system. In this demonstration we will discuss about how frequency of vibration affect the behavior of buildings. So in this demonstration we have two types of buildings. One is short building, another one is long building. So long building will have more natural period and short building will have less natural period. So when I am moving the ground slowly, so tall buildings get affected. If the motion is something like jerk, only short building get affected. As you can see in this one, so when the motion was just in the form of jerk, this short building fell down, and when the motion was very slow, tall building fell down. So this, let us see the natural period of the building in another demonstration. This is simple pendulum experiment. So here pendulums which are hung from the top, and as you can see length of each pendulum is different. So if I give a displacement to this pendulum and release it, so it is oscillating. So natural period of this pendulum is 1 to and fro motion. Now if I give the same thing to another pendulum and release it, as you can see this pendulum is oscillating in a faster manner compared to this pendulum. So that means what? Time taken for longer pendulum to go 1 to and fro motion is large compared to shorter pendulum. So that means what? Short buildings will have less natural period and long buildings will have more natural period. So if we come to this demonstration again, when ground motion is having long periods, tall buildings get affected, and when ground motion is having short period, something like this, short buildings will get affected. Now let us solve one example problem in this. So the details of a 3-story building with 3 meter by 3 meter plan area are as follows. Floor to floor height 3 meters, column dimensions 230 by 230, thickness of the slab 100 mm. So perform eigenvalue analysis and find out eigenvalues and eigenvectors by assuming columns are massless and infill walls are not present. So, let us first take, say, since all floors are similar, mass is 2250 kg. So, we are carrying the same example in this case also. Stiffness matrix we know, and then mass matrix also we know. So, eigenvalue performed in like week 7 module 2. So, we are using that. Now, eigenvalues we are carrying from that example. So, you can refer to the week 7 module 2 lecture. So, eigenvalues 1, 2 and 3 are 911.97, 7159.72, so 1,14,950.52. So, these are eigenvalues. So, if we take square root of that, we get natural frequencies. So, 30.198 radians per second first natural frequency, 84.618 radians per second second natural frequency, 122.272 radians per second third natural frequency. So, corresponding natural periods also we can calculate by using 2 pi by omega, t is equal to 2 pi by omega n, we can calculate that. And then eigenvectors are known values to us. So, we have already calculated this one in the previous class. So, we get natural period 0.2 seconds, 0.07 seconds and 0.051 seconds. So, 3 natural frequencies, and corresponding SD values from the response spectrum chart is spectral displacement 1 is 2.5 units, that is centimeters, and 1.75 centimeters, and SD3 1.5 centimeters. Then participation factor we can find out. So, participation factor 1 from the given mass matrix and vectors. So, first, second and third eigen values are modal vectors 1.22, minus 0.28 and minus 0.0027. So, usually if you add mass participations of all three, it should be equal to 1. So, in this case it is equal to 1. And then now we apply the equation of SRSS method. So, we substitute all the values, we get, so 1.489 meters displacement at ground floor, 2.462 meters at the second floor, 3.090 meters third floor. So, this is total displacement, that is the maximum displacement in response spectrum method. So, we can compare this with the maximum response of time history analysis, which is usually lesser than response spectrum method, because response spectrum method values are more conservative values. So, in summary, what we had discussed in this class is response spectrum method of analysis. So, usually time history response is done for important and critical structures when time history is available. If time history is not available and only response spectrum is available to us, so that also can give us fairly good results. So, results in terms of maximum displacement and maximum forces what might occur on the structure.